student at IISc, and he's Vamsi's student, and Vamsi will make him a presenter and he can do it. So he's going to speak about supercritical deformed Hermitian Yang Mills equation on compact projective manifolds.
Yeah, let me make him the go.
Yeah, once Vamsi makes him.
Right.
Yeah. So as soon as he shares his screen, he can begin. So he's a student, as I said, at IISc. The only course he has taken with me is probability models when I had a severe case of imposter syndrome teaching that course. But he's working with Vamsi, and you'll see what he's working on now. Okay, there he is. Yeah. Aashirwad, once you share your screen, you can start.
Is the screen visible?
Yeah, it is. And you can make it full screen. I think it's full screen. This is full screen. Yeah, you can start.
So we'll be talking about the deformed Hermitian Yang Mills equation on compact projective manifolds. Here the setting is that we have a first I'll talk about it on general Kähler manifolds. Most of the theory is the same as a projective manifold, but our results are mainly on the projective manifold. So the setting is that we have a compact.
Sorry, there's a bit of disturbance. Can everyone else mute, please? I think Harish and Ved are unmuted.
Okay.
Yeah, go ahead. Yeah, Aashirwad, go ahead.
Okay. So we have a compact Kähler manifold of dimension n, and we have a 1-1 real Dolbeau cohomology class. And the equation we wish to solve is this one, that the imaginary part of omega plus I into chi to the n, the imaginary part of this thing is equal to 0. What this says is that this n form is a multiple of chi raised to n times a constant times this constant. Now, as if we fix an omega naught in alpha, then by the del bar lemma, as Professor Ved was explaining, we can write any omega in the class alpha as omega naught plus I del bar of phi for a smooth real function phi. So this equation is actually a nonlinear second order PDE for phi. Now it's called like it shows up supposedly in string theory while when in mirror symmetry where you have where the special Lagrangian equation on one manifold gets transferred to the deformed Hermitian Yang Mills on the mirror manifold or something like that. And yeah, so that's the motivation for considering this equation. And okay, so to see what this equation actually looks like, we can choose coordinates of at a point such that the Kähler form chi is the identity form, and omega is diagonal with eigenvalues lambda I of x. If you do that, then at the point x, you have this expression for this this function. So it's equal to 0 if and only if theta hat is equal to the summation of theta I, the summation of theta I mod phi. So that's another way of writing this equation, and here theta I refers to the arc cot inverse of lambda I of x, and we're choosing the cot inverse to have its range in this interval. Now, as each arc cot, okay, we'll come to that later. So we get that summation of theta I, summation of theta I of x is equal to theta at each point x on the manifold, and this theta is congruent to theta at modulo pi. Okay. And it's called the phase angle. Now we look at some conditions which are necessary if we are to have a solution to the deformed dHYM equation. Firstly, because this thing should be equal to 0 for some omega in this class, the integral of the whole thing should also be 0. So that's one trivially necessary condition, and because we have this equation which is equivalent to the dHYM, and because each of these terms lie in 0 to pi. If you forget about any of those terms, then the sum of the resulting terms should be less than theta. So you also get this condition for any proper subset of 1 to n. So those are two necessary conditions if a solution is to exist. Now, like if this angle theta is in this range, then that's a more useful way of writing down both these conditions, but mainly this condition. So if theta is in this range, then sine theta is greater than 0. So we can divide. So if you expand this, you get real part of omega into real part of omega into sine theta minus cos theta into the imaginary part of this thing, and you can divide throughout by sine theta as it's non-zero to get this equation, and this one will be more convenient to work with. And it also shows that cot theta depends only on the cohomology classes of omega naught and chi. Yeah, and we also have to reformulate this inequality. So if you take k to be a singleton, for example, I of x is less than theta for all theta. Now, since theta I and theta are both are both in 0 to pi, and since cot is decreasing, we can apply cot to both sides to get lambda I greater than cot theta. Now this is the same as omega greater than cot theta times chi, because if we choose if at a point x we choose basis where chi is the identity matrix and omega is diagonal, we basically this thing is basically the same as this thing, and this and a similar thing works for all subsets K, which are proper subsets, so that you get an inequality. Yeah, if you like apply the same logic, you can show that this inequality is equivalent to this thing, to this set of inequalities. So like for k equals 1, we've seen that you get this inequality, and for k equals 2, you get this, k equals 3, you get this, and so on. Now so that's one reason for considering the super. If we restrict theta to be in this range, we say that the angle is supercritical, and this is one the reason it's useful is because we can reformulate the condition these conditions in terms of the forms omega and chi. Now it was proved by Cohen, Jacob, and Yao that when theta is in this range, you can find if when theta is in this range, if you have an omega satisfying these inequalities, and this one, but this depends only on omega not. If you have such an omega, then you're guaranteed a solution to the dHYM equation, and such an omega is called a subsolution of the dHYM equation. So Cohen, Jacob, and Yao showed that the existence of a subsolution is with the existence of a subsolution is equivalent to the existence of a solution when the phase angle is in this range, these conditions are also called Cohen conditions, like similar to the dHYM criteria. In the dHYM thing, omega is positive for all things, but anyway, it's called the Cohen condition because it's closed under convex combinations. If you take one omega satisfying these inequalities and an omega 1 satisfying these inequalities, and omega 2 also satisfying these inequalities, then t omega plus 1 minus t omega 1 plus 1 minus t omega 2 also satisfies these inequalities. This follows from the results of Yuan. So it's called the Cohen condition, and if omega and if omega is very large, that is if its eigenvalues are all very positive very are positive and very large, then it's also easy to show that these inequalities are satisfied. Yeah, so that's the Cohen condition, and Burns Jacobi showed that the Cohen condition is equivalent to the existence of a solution when theta is in this range. But this is not the full supercritical range, so so that problem was still remaining.
Can I interrupt for a few seconds?
Yeah.
So I'm not hearing clearly. You were talking about a condition. So there is pound of dHYM, and then you're talking about a Cohen condition. So the phrase where you say condition, are you saying pound condition or Cohen condition?
Cohen condition.
Cohen condition. Okay, thanks.
Oh.
This basically comes from dHYM, right?
Like the thing I'm getting to where we show that the existence of a solution is equivalent to some numerical criterion that comes from.
All right, thank you.
Yeah, and Collins Jacob and Yang also conjectured that if you have some numerical criteria similar to the ones approved by Demay and Pon, you also get those numerical criteria should also be equivalent to the existence of a solution. Now, when M is projective, you can write these conjectured numerical criteria as these inequalities, where V is a k-dimensional variety. And Professor Baird was talking about this. For general Kähler manifolds, you will have an extra term. This time, this thing wedged with this some power of chi. That thing should be positive, but our main interest here is in the projective case, and in the projective case, these inequalities. Yeah. So now, like a major advancement towards this result was made by Gao Chen, where he showed that if you replace the zero by some epsilon times the integral of chi raised to k, the so-called uniform positivity condition, then that condition is equivalent to the existence of a solution. And yeah, and the way he did this was first, as Professor Ved was explaining a bit, you consider the product of M with itself and use a concentration of mass technique to produce a current on M cross M, which has some mass on the diagonal, which means that the current should be greater than some positive multiple of the current of integration along the diagonal. And once you do that, you can roughly you can integrate along. You can push forward T to get a current on the diagonal which satisfies the Cohen condition. That was how Gao Chen did it. that was how he produced the current. And once he had the current, he used a regularization to patch this current with 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 a smoothing obtained on some neighborhood of a Lalong sublevel set of T. So if T is the current, then its Lalong sublevel sets are analytic sets. This follows from proper analytic sets. This follows from theorem of CO. So if you have and because these are proper analytic subsets, you can apply induction on the dimension of this set to obtain a current, to obtain a smooth solution on this subvariety if it's smooth. If it's non-smooth, you'll have to use resolution of singularities or something. It's somewhat more complicated. But if it's smooth, you get a solution on this subvariety which satisfies the Cohen pattern. You get a form on the subvariety which satisfies the Cohen condition, and you can it's not hard to extend this thing to a neighborhood of that subvariety, and once you have that, you can glue that with the current T. Like roughly, that's how he did it. And yeah, right. Yeah. So the concentration of mass here refers to use concentration of mass instead of setting the instead of just considering this equation with the RHS being 0, you consider it with the function f. Yeah, and you consider a family of such equations for T in some interval on something, for T on some interval, and as each of these FTs will be smooth, and if for each T you have a solution to this equation, then the limit as T approaches 0, if for each T you have this solution, then you can show using Banach Alaglu that by weak compactness there exists a current which is a limit of these solutions, which also satisfies the Cohen condition in some sense. Like you can't speak of the Cohen condition for currents directly. So if you can have it make sense, and if the limit of the weak limit of these solution of some subsequence of these solutions will be a current satisfying the Cohen condition, and its mass will be concentrated on the subvariety. If on the subvariety, if you take these FTs, if you take these functions of probability. So there's some there's some importance in considering the dHYM equation with whose RHS is non-constant, and that's basically the twisted dHYM. This one, yeah. Now, as I mentioned earlier, Gao Chen showed that uniform positivity is equivalent to the existence of a solution. Recently, Chu, Lee, Takahashi proved that the uniform condition can be removed for the dHYM equation, and they used the method of Jian Song, who also used the method of Gao Chen and solved the J equation without the assumption of uniform positivity. And yeah, and like we proved that
Okay, it's unstuck now. Go ahead.
time's up.
Or it
Okay.
might be my problem. Sorry.
Okay. So basically, we proved that the twisted dHYM equation can also be solved on projective manifolds, provided the this positivity condition is satisfied. And yeah, how much time do I have left?
One moment, I'll check 11. I lost the schedule.
The next talk is at 11:45, Aashirwad. So you have actually 5 minutes or so, technically.
Yeah. Yeah. So this as I explained, there's interest in considering the twisted dHYM equation, where instead of zero you have a function f on the RHS, and we showed that this equation can be solved provided the positivity the numerical positivity condition mentioned earlier could be shown. Yeah, and Gao Chen had already solved this equation for dimensions larger than 3, but his proof only for n larger than 3. For n equals 1 and 2, like the proofs are trivial. For n equals 3, it's a bit more complicated. Yeah, so that's what that's the work. And to we use the continuity method. We consider first we make a substitution from omega, which instead of considering the equation for a small omega, we let capital omega be this expression, and so in terms of capital omega, the Cohen conditions can be written as these two conditions, and you get a similar and the dHYM, the dHYM equation also changes, and we consider a continuity path. They use the method of continuity along a path which looks something like this, and for this we follow the proof of Professor Vamshi. Yeah, and to use the method of continuity, you have to show that as we have to solve this family of equations for each t, and we have to show that the set of t where has solutions is both open, closed, and non-empty. Like openness is uh, mm, is standard, and the fact that it's non-empty follows from Gao Chen's result, and we can also show that it's closed through some involved calculations. And once we've done that, we can apply the results in the paper, of Professor Ved and Vamshi on the generalized Monge-Ampere equation to show that we can use a similar approach to show that on a projective manifold, the non-uniform positivity condition is equivalent to existence of the solution. That's it. Thanks.
Okay, thank you very much. Let's thank the speaker. Are there any questions? Okay. If not, we finally have a short